When computers send and receive data from each other over radio waves, they can run into a problem called channel noise. This is a very interesting problem, as is the method that engineers used to solve it. When computers send data to each other wirelessly, they need to send bits of information, a sequence of ones and zeros that can be interpreted into letters which compose code. They do this by sending a sequence of radio pulses that are either high amplitude or low amplitude. This method is known as shift keying. If we want to send the binary number 01001011, which is read as the letter K in Unicode, we do this by sending a pattern of radio pulses. Ones with high amplitude are interpreted as a 1, those with low amplitude are interpreted as a 0. So keep in mind, whenever you see a 1, that's a high-end radio pulse, and a 0 is a low-end radio pulse. For this binary number, our wireless transmitter would send a pulse sequence of low, high, low, low, high, low, high, high. Now the problem with this method is that these messages can be susceptible to background noise. The universe is filled with radiation of many different frequencies and amplitudes, and while it's unlikely, it is possible that one of these wayward radio waves could hit the receiver at the wrong time and flip a 1 to a 0 or vice versa. In our binary number, if this 0 here were flipped to a 1, we would go from having a K to having an O. When it comes to computer code, a single letter being wrong can cause the entire thing to fall apart. So reliability is key. Now here's the workaround. Instead of sending a single pulse for each binary digit, send 2. Before, in order to represent a 1 in binary, we sent 1 high pulse. And in order to represent a 0, we sent 1 low pulse. Now, in order to represent a 1, we must send 2 high pulses, and for a 0, 2 low pulses. We then program the computer on the receiving end of this signal to only expect pulses in pairs. If, for example, we want to send the number 1101, instead of sending high high, low high, we send high high, high high, low low, high high. This way, if any interference occurs, and say this low pulse was flipped to a high pulse, the receiving computer notices that a 1 and a 0 are in the same pair together, which isn't supposed to happen. It can then request that the data packet be sent again. This method is what's called repetition code. As unlikely as it is that a single pulse will be misrepresented, it's even less likely that 2 adjacent ones will be misrepresented. But it's still not impossible. So what if we send 3, or 4, or 5, or even 10 pulses per digit? The more pulses required to represent a single digit of binary, the more reliable it becomes. Better yet, if the computer requires 10 pulses for each digit of binary data, we can tell it that if a single one of them is wrong, then just go with the other 9. It's extremely unlikely that in this example here, all 9 of the low charges were tampered with, while only the 1 high charge was correct. This method is called majority logic decoding. Another approach to this method is to send exactly the sequence of binary we want, but send it 3 or 4 or more times. So if we wanted to send a binary number like 1001, we send high, low, low, high, but send that same sequence 3 or more times, and program the receiving computer to expect such. If any of them are wrong, the computer knows that something went wrong and it needs those packets to be sent again. So while sending more pulses per piece of data is more reliable, the downside is that the more you have to send per piece of data, the longer that piece of data takes to send. Using a 1 pulse per digit method means we would only need 8 pulses for a byte of binary, while using the 10 pulse per digit method means that we would need 80. Thank you for watching, and liking, subscribing, and commenting is a great way to support the channel. And as always, I hope I helped.